And so that's what we're going to be doing this week, measuring the mass of the Earth. So what we're going to do for this activity is we're going to use the fact that gravity exists on the Earth and that the motion of stuff on the Earth is influenced by gravity, and Newton's second law, which tells us how forces affect the motion of things, to determine the mass of an entire planet by just simply dropping marbles. So what you're going to need for this activity is you're going to need something to measure distances, a meter stick or a tape measure or something like that. Something that can measure in meters would be great. If you measure in feet, you'll have to convert to meters, because this only works the way we have it laid out if you use the metric system. But you can look up the conversion factor online. You need a stopwatch. Any sort of device that has a stopwatch on it will work. And you need a marble or something small and relatively heavy to drop, a ball of clay or something like that. You want it to be kind of heavy so that it and small so it can overcome the air resistance, and that plays a pretty minor role. You don't want to drop like a coffee filter or something like that, because that won't that'll float down on the air currents instead of dropping by minimizing that. So what we're going to do here is try to find a place that's at least 2 to 3 meters high. The taller the better. If you can get up off the ground, if you've got a third-story balcony on your apartment or something you want to use, that works out great. Just be safe. Don't climb, any massive trees or anything like that. But the further off the ground you can get, the better the result is going to be. So 2 or 3 meters off the ground. If you get up too high, like if you went to a 12-story building, the object will reach terminal velocity before you hit the ground. And you'll mess up your results, and you might kill somebody by dropping a marble off a 12 story. So keep it like 3 to 4 meters tall. You can measure this height by dropping a string over the side and getting a length of the string, and then measure the length of the string to figure out how high you are. And then what you're going to do is you're going to drop a marble from the same height a bunch of times and time how long it takes to fall. So it'd be helpful if you had a friend there to help do the timing, just so you can drop it and then they can hit the stopwatch when it hits the ground. You can do it by yourself if you've got some good coordination. That'll work too. So what you're going to do is you're going to take these recordings. All the data you're going to take is simply measuring the time elapsed between when the object leaves your hand and when it hits the ground. And you're going to record those on your data sheet. You're going to do this 20 times. Now, why are we going to do this so many times? Basically to help remove any random errors, or at least average out random errors that occur on your when you're dropping this. If you slightly release the ball too early or too late, hopefully that'll be random and it'll work itself out. But if you think about it, there's also 50 of us in this class, right? Each one of you is going to do this 20 times. So 50 times 20 is 1,000, right? We're going to be able to average 1,000 different measurements to get this result. So when you guys send all your stuff to me, I'm going to compile the results and make a result for the entire class on this measurement of the mass of the Earth, and we'll see if we can get really close to the right value. And this will hopefully demonstrate why scientists always take so much data. You can really improve your chances of getting an accurate result if you take a lot of data. But rather than have you do 1,000 trials, you can do 20, and we'll have 50 people turn them in. Okay, so how does this work? What do you get from this time? Well, if you look right here on the activity, when you're measuring the time right here, we know that the position of an object, and I can just write this down, the position of an object, we can relate that to its acceleration through 1/2 a t squared, right? So if I measure the amount of time that has elapsed and I measure how far it drops, I can get the acceleration. So I rewrote that like this, and it's negative just because we're falling down. That's just the convention. If I measure the time down here, right, which you're going to get from your data chart, from your averages, and if I measure the distance, which you're going to get from your string when you measure how high you're dropping the marble, I can divide the distance divided by t squared, multiply by 2, and that's going to give me the acceleration. So the acceleration is the thing that we're measuring. We're measuring how much the Earth's gravity is pulling on this object. Once we have that, we can combine a couple of things. We can combine Newton's law of gravity, gmm over r squared, with Newton's second law, F equals ma, and if I put those things together, I can say F equals ma, which is equal to g m over r squared. You'll notice that the little m's cancel out, so the acceleration is independent of the mass of the thing you choose. So we don't even have to measure it because it falls out of both sides of the equation. The reason for that is because, yes, the gravity is pulling on a more massive object harder, but the inertia of that object resists the motion more, and so you wind up with it canceling out. And if I take this a equals gm over r squared and rewrite it, I get the mass of the Earth in terms of the distance and this constant g and the acceleration that you're going to measure. Okay. So this will give you the mass. The only thing we need to know here that we can't measure directly ourselves, at least not yet, is the size of the Earth, the radius of the Earth. However, a little bit later we are going to measure the radius of the Earth, or at least talk about how it is measured. So that is something that you personally can measure if you want to go through the activity. But we're just going to look it up in our appendix. The radius of the Earth, it's actually given right here. The radius of the Earth in meters. G, which is something we've measured, scientists have measured over the last 300 years. Again, all in metric units. So if you measure your acceleration needs to be in meters per second squared, which means you need to measure x in meters and measure your time in seconds. Okay, so once you've got all that, you can run through those calculations, and what you should end up getting is an estimate of the mass of the Earth, right? And I can just kind of show you, from my experience, if I were to drop an object from about 2 meters, it takes a little bit less than a second. So let's imagine, just to do this calculation to see how it goes, let's just imagine for the sake of argument that my average time is like 0.8 seconds. Okay, so I'm just making this up to show you how the math works out. To figure out the uncertainty for that, if I've got all these different measurements, I can toss out the longest and shortest times and then use the next longest and shortest times, subtract those and divide by 2 to get an uncertainty. And let's say my uncertainty, if I do that, turns out to be like plus or minus 0.01. Okay, that's how well I've measured this. So I want to take this average time and square it, the first thing. So I take out my calculator here and go ahead and do my average time squared. So it's 0.8 seconds times 0.8 to square it gives me 0.64. So this is 0.64. And if I want to solve for the acceleration, remember I said that for this particular example, I'm dropping this from 2 meters. Right, so I'll say 2 meters there is my distance, so that's going to be my x. So this is my x right here, 2 meters. So I take 2 times 2 meters, which should be 4. 2 times 2 equals 4, and then I divide that by my value for t squared, which is going to be 0.64. And that gives me an acceleration of 6.25 meters per second squared, which is not the 9.8 that we would expect, but again, if I'm only dropping it from 2 meters and timing it myself, that's the best I can do. But we're going to be putting all of these values together, so we'll see how this comes out. And this is negative just because I've got a negative sign here. It's negative because gravity pulls down, and by convention up is positive and down is negative. But the negative sign is just telling us that it goes down. You don't need to use this negative sign for the next step, because that negative sign will that's just telling you the direction, and we don't need that for the mass. So the final step then is to calculate this guy right here, right? So I know my acceleration now is 6.25. 6.25. That's my acceleration right there. The radius of the Earth was 6.378 times 10 to the 6, and that's squared. And then I divide that by g, which is 6.67 times 10 to the minus 11. Okay. So I've got to just do this calculation now, so I've been using Google Calculator a lot lately. 2 plus 2, it should fire up calculator for me. There we go. Okay, so I'm just going to type this guy in here. 6.25 times 6.378 times 10 to the 6 squared. So if I do that, should get that number. Well, divide that by g. So I take that number and divide it by 6.67 times 10 to the minus 11. Perfect. Okay, so I get 303.8 times 10 to the 24. So let's do that one more time so we make sure that's clear for everybody. I'm going to take 6.25 times 6.378 times 10 to the 6 squared, and then that whole thing is divided by 6.67 times 10 to the minus 11. And that should give me 3.8 times 10 to the 24. So let me write that down. So 3.8 times 10 to the 24 goes here. 3.8 times 10 to the 24 kilograms. Okay, so that's the calculation that we go through. Now you'll notice that the measured value of the Earth is 6 times 10 to the 24. But with this, I'm going to get within a factor of 2 just by dropping marbles. And hopefully, if we do this 1,000 times, because all of you are going to have 20 measurements times 50 students, we'll be able to get a much closer value. Okay, so that's the plan for this activity. We're going to go through the measurements. You'll take these observations, you'll do the calculation and answer a couple questions, and then once you've given me all of that information, I'm going to collect it in a big spreadsheet and publish it to see if how the results turn out. Okay, so I think that's all I've got for us today. If there are no more questions, I think we'll just wrap up and see you on Thursday.
John, is that Google Calculator just you look on Google and bring it up?
Yeah, so it's funny, if you do a Google search on Google Calculator, it's hard to find, so I usually just bring it up by typing 2 plus 2 in the search bar, and it brings up the calculator.
Oh, okay.
And I like Google Calculator a lot because it lets you kind of see how the scientific notation works. When you're doing it on your calculator, the order of operations can be kind of tricky. So I like Google Calculator because I can say 6.67 times 10 to the minus 11, and the way I get that to the minus 11 part is I use the little caret symbol. It's like shift 6 is how I get that. And then if you miss something on the front of this, you can continue to type and say, well, okay, I'm going to make this times 100 divided by 2. So you can just see what you're doing as it goes through there. So I like Google Calculator, and then always know you've got it someplace if you've got a computer handy.
Right. Okay. Great.
All right, cool. Any other questions, Shay, before we get going?
No, that's it. Thanks,
All right.
John.
Hey, we'll see you on Thursday.